Welcome to qnawire.
In this question, the main idea that we want to drive across is a correspondence between the quantum picture to a classical picture. Right, so for a quantum picture, usually we have something that is quantized, so such as the angular momentum, the energy, and we have some corresponding quantum number associated, right, the n value. Now what we want to show is that when n goes to infinity, this will correspond to a classical picture. Right, so this is the correspondence postulate, and the thing that we are interested in for this question is the frequency of radiation that is being emitted by an atom. So the frequency in the quantum picture is basically due to the energy difference between the energy states. This will correspond to the energy of the photon, so lambda is equals to c over delta E. On the other hand, for the classical picture, the frequency of radiation is actually the frequency of electron that is orbiting around its orbit. So the frequency of the electron orbit, this goes to 2 pi r, the radius of the orbit, divided by the velocity of the electron. So this is the circumference divided by the velocity, which will give us the period, and therefore the frequency is just 1 over period, just Vn over 2 pi Rn. Right, so we want to show that there is some connection, right, between the wavelength over here, where we can then find the frequency, which is equals to c over lambda, right. We want to find whether there's a correspondence between these two very different pictures, right, of the radiation when n goes to infinity. Now we're going to start off with the classical picture, right, of the electron orbiting, and to find the frequency we just have to substitute in the velocity of the electron as well as the radius of the orbit from the Bohr's model. So from the Bohr's model, Vn E square over epsilon naught times 2nh, whereas Rn as epsilon naught n square h square over pi times m times E square. You can find the frequency. We can cancel out the common factors, the pi. Sorry, there's a missing pi over here. Right, this is 2 pi times Rn, so there's a 2 pi over here. We can eliminate the pi. We bring down the h and we bring down the n. This will be n cubed h cubed. We bring the m up to the numerator. We bring the e square up as well to the e square here. The 2 and the 2 will multiply together to get 4, and the epsilon naught will multiply together to get epsilon naught square. So what we get is b e4 times m divided by 4 epsilon naught square, and we have n cube h cube. Right, so this is the expression that is actually shown in the question. So this is frequency of the orbit, so equals to frequency of the radiation emitted in the classical picture. Now moving on to the quantum picture, right? The quantum picture tells us that, right, from previously shown over here, the frequency is equals to delta E over H. Now what is delta E, right? Delta E is the energy between the two energy states. So we have to consider two energy states, En1 and also En2. Now from the Bohr's model of the energy, En is equals to negative 1 over epsilon naught square me to the power 4 divided by 8n square h square. So if you have these two different energy levels, right, supposing that this is the higher energy level, right, the energy difference will just be 1 over epsilon naught square me4 by 8h square, and we will have 1 over n1 square minus 1 over n2 square. Right, so this will be En2 minus En1. Now we will simplify this picture a bit by assuming n2 is equals to n plus 1 and n1 is just equals to n. By simplifying this, we can evaluate this fraction over here. So it'll be 1 over n square minus 1 over n plus 1 square. What we get by combining the fractions together, to be equals to 2n plus 1 divided by n square times n plus 1 square. Now comes the crucial part, right? The crucial part is when we have n goes to a very, very large number, right? N goes to infinity. What happens to this fraction? So 2n plus 1, because we are adding 1 to a very, very large number, this just approximately goes to 2n. Right, we can ignore the extra 1. Also, n plus 1 just approximately equals to n. So what we get from this approximation is 2n at the top and n square times n square. This will be 2 over n cube when n is very, very large. Now we can substitute this thing back into this equation. We will get this factor, right, which is me for epsilon naught square times 8h square. picture. Multiply this with our factor over here, which is 2 over n to the power 3. This is our delta E. From here we can find what is the frequency by dividing delta E with h. And I think you can see that this to cancel, get 4. So this ME4 divided by 4 epsilon naught square. We have n cubed, we have h square, but h square with an extra h from here, then h cubed, n cubed. This is the frequency in the classical picture. And this actually shows the correspondence principle, right, between the quantum picture and the classical picture.